and we are moving on to chapter 29. So talking about, last chapter 28 was really about forces on moving charged particles. Now we're going to talk about magnetic fields due to currents. The fact is, anytime you have a moving charged particle, that creates its own magnetic field. Okay, and so we're going to take a look at that. There are different geometries of current and the types of fields that are produced. There will be a B field quiz. This is your last field quiz, right? We had the I quiz, we had the E field quiz, the E chart quiz. And so you can see the different types of geometries, things. You know, if you have, first of all, a bar magnet, and then we have what's, you know, a solenoid. Solenoid is, it's kind of like a coil, but it's lined up. A coil usually is just wires wrapped around. It's not anything where, you know, it looks like a cylinder, like that solenoid thing. Just a ring is there. If you have a coil wrapped around a piece of iron or something like that, it'll set up a magnetic field in the iron. Or even just a wire by itself. That's the most basic one. A wire by itself produces a magnetic field around the wire according to the right-hand rule. Okay, and so let's put it this way. So magnetic fields are produced by moving charges. That's the basic idea here. And this is the Biot-Savart law to find the magnetic field due to any point. And you know, simply put, dB, some small piece of the magnetic field, is due to some small piece of the current, and it's given by mu naught over 4 pi. Mu naught, by the way, is the magnetic equivalent of epsilon naught. Remember, epsilon naught was the permittivity of free space. Mu naught is called the permeability of free space, and that's 4 pi times 10 to the negative 7th Tesla's meters per amps, or Weber's per amp meters, right? There's so many different units that we've come up with by now. And so, so B is given by mu naught I over 4 pi, and then the integral of ds over r squared, and that is a cross product with r hat, the vector, the radius vector from the wire, whatever is carrying that current. And so the direction of a magnetic field is given by the right-hand rule. What you do is you stick your thumb in the direction of the current, and then these fingers, your other 4 fingers, are pointing in the direction of the magnetic field. It actually produces a magnetic field in a circular kind of way, right? So the magnetic field arrows are pointing around the wire and in the direction of the magnetic field. Okay, so the magnetic field of various geometries from a thin, straight conductor of finite length would be mu naught I over 4 pi a times cosine theta 1 minus cosine theta 2. All right, that's it. But then if this thing is infinitely long, then you end up with 2, because the cosine of theta 1 is 0 if that thing is infinitely long, and theta 2 ends up being pi, right, or 180 degrees, and so you end up with 1 minus negative 1, so that's 2. So the geometry of a wire of infinite length is mu naught I over 2 pi a. That would be a good one to have memorized, because we're going to see it quite a bit. For a semi-infinite conductor, so you're at one end and then the conductor goes on forever in the other direction, that's mu naught I over 4 pi a. And that would be good to remember as well, because we're going to see situations like that. You know, when would we use that? Well, if you've got a wire coming up and then taking a sharp turn, you want to know the magnetic field due to this piece here, if you're over here. And so, example 1, calculate the magnitude and direction of a B field due to a long, that's code for infinite, so watch out for those types of things. Straight wire carrying 5 amps to the north at a distance of 4 centimeters. All right, and all you're doing here is you're taking mu naught I over 2 pi a, the formula, and you're plugging in the numbers. Mu naught 4 pi times 10 to the negative 7th times 5 amps over 2 times pi times a, which is 0.04, and you should end up with an answer of 2.5 times 10 to the negative 5th Tesla. That's it. I'm not even going to write it down. It should, you're just plug and chug. Okay. Example 2, we're going to skip for the sake of time. You don't necessarily need it. But let's take a look at example 3. It says calculate the magnitude and direction of the B field at the point P as shown, and here the answer is 0. If you look at the formula for a finite line, mu naught I over 4 pi a cosine theta 1 minus cosine theta 2. Theta 1 and theta 2, if you draw those, they're actually the same. They're both 0. And so you get cosine of theta 1 is 1 minus cosine theta 2, which is 1, so it ends up just being 0. So this is important. If you have a wire coming this way and a point here, the magnetic field here due to this wire is 0. The only time we get a magnetic field is when we are off of the length of that wire, that axis that wire is on. And so now C, so we're looking at this loop, right? This sort of circular loop from this thing. All right, so if we've got, let me do this way. If it looks like this, at this point, remember what we just said, magnetic field due to this wire is 0, the magnetic field due to this wire is 0, due to this wire is 0, and this one. So the only magnetic field we're getting is due to this arc. Okay, and that's given by mu naught I over 4 pi r times theta. Okay, where theta is in radians. If you have a current loop, so that thing goes all the way around, then theta ends up being 2 pi, and so it ends up as mu naught I over 2r. And if you have multiple loops, so if you have a wire and it's just wrapped around a bunch of times, again, not a solenoid where it looks like a cylinder, but just a circle wrapped around a bunch of times, a coil, then it ends up being mu naught I over 2 pi r times n, where n is the number of loops. You're just taking, the formula for one loop and multiplying it by the number of loops. And then if you're some distance away from the axis of the circle, right, from the center of the circle along the axis, then that's given by mu naught I r squared over 2 r squared plus x squared to the 3/2 power. And then again, if you have n loops, then you just multiply that by the number of loops that you have. Really simple. We're not going through the derivations for these because you don't really need them. All right, so here's example 4. Let's take a look at this. These are mostly just plug and chug problems. All right, so it's a circular coil of wire and it has 10 turns. The current is 0.3 amps. And so for part A, we want to know the magnitude of the B field at the center of the loop. So that's just mu naught I n over 2r. So you plug in your numbers here, right? I is 0.3, n is 10, r is 0.1 because it's 10 centimeters. And so this should end up as about 1.9 times 10 to the negative 5th Tesla. I also have written down 1.88, so should be close to that. Pretty straightforward. Now we want to know the magnetic field 1 meter from the center of the loop along the axis of the loop. So that is this formula now. Mu naught I n r squared over 2 times r squared plus x squared to the 3/2. All right, and again, we're plugging in our numbers. The only different number we have now is x, which is going to be 1 meter from this coil. And this should end up being about 1.86 times 10 to the negative 8th Tesla. So you can see much smaller there. And then we want to know the location where the magnitude is half of the answer in part A. So where is it? In other words, where is this? Then it's half of this, so this is going to be mu naught I n over 4r, right? So this is half, so the 2 gets multiplied, equals mu naught I n r squared over 2 r squared plus x squared to the 3/2. Now, this cancels out with this, and so I can do some rearranging here, and I'm going to get 2 r squared plus x squared to the 3/2 equals 4 r cubed. This 2 can cancel out with this, so I end up with a 2 there. All right, so now I'm going to take this to the 2/3, or to the 2/3 power, everything. And let me go up here so I have a little more room to work. So I'm going to have r squared plus x squared equals r squared times 2 to the 2/3 power. All right, so now I'm going to subtract this over to this side. So I'm going to have x squared equals r squared 2 to the 2/3 minus 1. We're just subtracting the coefficients on the r squareds. And so then x is going to be r 2 to the 2/3 minus 1 to the 1/2 power. I plug in my value for r, and I'm going to get about 7.6 centimeters. Okay, great. So now we're going to look at 29.3. The fact is then, since a moving charge creates its own magnetic field, now two wires can create a force on each other. All right, so if I have a wire here and a wire here, and they both have current going in the same direction. Okay, so now we're going to look at the force. Let's say the force on this wire due to this one. So we're going to do, here's 1, here's 2. So this current is producing a magnetic field this way into the board. Right, like that. So this is the magnetic field of 1, of this wire. So now I've got a force, IL cross B, right, IL cross B. This produces a force that way. Right, this is the force of 1 on 2. Interesting, right? Okay, so now this one produces a magnetic field like this. I'm going to stick my thumb in the direction of the current. This is, so on this side of the board it's coming out. So this is the magnetic field due to 2. And so current is this way, magnetic field is that way. This is producing a force that way. So these two wires are attracted to each other. So here they're going in the same direction, and then they attract. This is pretty much the only time where you have two of the same thing attracting in physics. Most of the time, the two like things repel. And so now we want to know what is the force? What's the magnitude, you could say? So the magnetic field due to each wire is mu naught I over 2 pi a, where a is the distance between these wires. All right, and the force is IL cross B. But again, B is this, so it's IL times mu naught I over 2 pi a. Okay. And so this, this is I1, I2, whatever it's going to be. So, well, so that's it. L, I1, I2, mu naught, right, over 2 pi times the distance between them. This is the force between the two wires. All right, so now what about what if they're going in opposite directions? So in this case, here's a wire, current is that way. Here's another wire, the current is that way. We'll call this again 1 and 2. And so then this wire is producing a magnetic field into the board. So here's the magnetic field due to 1. And then the current is going that way. The magnetic field's into the board. So that means there's a force this way. So here's the force of 1 on 2. This wire now, I put my thumb in that direction, going down, and it's producing a magnetic field this way. So here, this current is producing a magnetic field into the board. So this is the magnetic field due to the current in wire 2. And so then IL cross B, right? B is into the board. This creates a force that way. It's a force of 2 on 1. Okay. So then example 5, calculate the magnitude and direction of the B field midway between the long wires. If I1 is 4 and I2 is 8 and A is 1 meter. All right, so B is mu naught I over 2 pi A. Right, but what are we looking at here? We're looking at A over 2, right? And so the total magnetic field will be the magnetic field of 1 plus the magnetic field of 2. So this is mu naught I over 2 pi A over 2, that's the distance, plus mu naught I, I'll call it I1 and I2, over 2 pi A over 2. And so what this is turning out to be, so what direction are these? Well, if I have this current going that way and this current going this way, this one's producing a magnetic field into the page, right? So that's B1. And then this one is also producing a magnetic field into the page. So that's why I'm adding them up. Okay. And so I think this is going to end up being, right, I have a common denominator, so it's just, I'm adding up the top part. So it's going to be mu naught 4 amps plus 8 amps over pi times 0.5 A over 2. A is 1, and I'm dividing that by 2. 2 pi A over 2. Okay, and so when I do this, I think you should end up with 4.8 times 10 to the negative 6th Tesla. All right, that's our magnetic field at that point. Now in example 6, I've got, these are our two wires, again, 4 and 8 amps, like before. We'll call this I1, and this one's I2. And so let's take a look at where, we want to know where's the magnetic field going to be 0. Again, this one, the magnetic field due to this one is into the page. That's B1. And over here, B1 is also going to be into the page. But here, B1 is going to be out of the page. Okay, now this one, on this side it's into the page. So this is B2. And on this side, here it's coming out of the page. So this is B2. Sorry, out of the page like that. On this side, B2 is always going to be bigger than B1. But over here, right, as I get really far away from this, this is the larger current. B2 is eventually going to be bigger. Here, when I'm close, B1 is larger. But as I get away, B2 is going to be larger. And so the place where it's 0 is going to be somewhere on this side over here. Okay. And so the way that I'm going to set this up, so I'm going to be subtracting these. 0 is equal to mu naught times 4 over 2 pi d. I'm going to be some distance away from this, right? Minus mu naught times 8 over 2 pi d plus 1. Because the distance from this wire is d plus that 1 meter. Okay. So now I'm going to do some simplifying, and we'll see what happens here. 4 over d is equal to 8 over d plus 1. So 4d plus 4 equals 8d. So 4 is equal to, subtract that, 4d. So 1 meter is d. So 1 meter from this wire is the place where that magnetic field is going to be 0. Okay, so 1 meter to the left of current 1. Now in this case we want to know where's the electric field or the magnetic field going to be 0. And so they're both going in the same direction. So everywhere to the right is into the page, right? So here's B1, B1. To the right of this one is into the page, B2. But here coming out is B2. And so here both are coming out of the page. And so this is my only candidate for some place where the magnetic field is going to be 0. And I imagine it's going to be closer to this one. That magnetic field is weaker than this one. So probably somewhere in this area. And so we can call this distance d. Okay. And so again, 0 equals 4 pi, or mu naught I, so we'll call that 4, over 2 pi times d, minus mu naught 8 over 2 pi d minus, or rather 1 minus d. Right. The distance from here is the 1 meter minus that length d. And so I do some canceling out, some simplifying, I end up with 4 minus 4d equals 8d. So it ends up being 4 equals 12d, and d is equal to 1/3 of a meter. So this means that I'm a distance 1/3 from this current carrying wire. That's where the net magnetic field is 0. Okay, so example 8, what we're looking at here is adding up these forces, because I have a current carrying square next to a current carrying wire, and I want to know what is the force on the rectangular loop based on the given dimensions. We have this formula from before, or let's just take a look. So here's the 30 amps going that way. And so this is going this way, that's 20 amps, here, here, and here. So first of all, the current, we're looking at the force on this, the net force on this thing. So this is producing a magnetic field into the page below. All right, so that's magnetic field due to the 30 amp wire. That means I've got current here, right? Current here, magnetic field that way. There's a force here this way. There's also a force that way, right? I cross B, so there's a force that way. There's a force this way, because if I go that way and then curl with the magnetic field right into the page, then I get force going down. And here, that going that way, up, cross into the page, and then there's a force going that way. These two forces cancel out because they're symmetric, but this one is going to be a little bit weaker than this one. This one's stronger because it's closer. Okay. And so what I do is I calculate this force, and then I subtract that force, and that's the net force. And we came up with a formula before, mu naught I1 I2 times L over 2 pi A. Right? And so all I'm doing is now I'm plugging in the numbers for this wire, plugging the numbers for this wire, and then that'll give me two forces, and that'll be the solution. Okay, so I'm going to do the force at the top minus the force on the bottom, and so it's going to be mu naught, let's see, 30 times 20 times, now for the top this is 10 centimeters. Yeah, this distance is 0.01, or no, that's the one on the bottom. Oh, the length here, sorry, is 10 centimeters, so that's 0.1 over 2 times pi times 0.01. All right, and then this is going to be, or minus the force on the bottom one, so that's mu naught 30 times 20, it's the same current, times 0.1, right, the length of the wire is the same, 10 centimeters, over 2 pi, and this is 0.09, because this is 0.01, that's 0.08, so you add these two up, you get 0.09. When you do this whole thing, don't forget mu naught is 4 pi times 10 to the negative 7th. And you should end up with a net force of about 1.06 times 10 to the negative 3rd newtons. And that's it.